Hi, everyone. My name is Thomas, and together with my colleague Ingvar here, we're going to show you how using WebAssembly can speed up your computationally intensive workloads by more than 10x, and how using modern WebAssembly tooling can let you take advantage of WebAssembly more easily. We'll start by reminding everyone what WebAssembly is and showing some of the improvements we've been making to Chrome's implementation. Then we're going to get into some of the different language features that are starting to ship as part of WebAssembly. And then finally, we'll close out by covering some of the new tooling updates that have been coming as well. So let's start by reminding everyone what WebAssembly actually is. WebAssembly is a new language for the web that is designed as a compilation target to offer maximized and reliable performance. It's important to remember, though, that WebAssembly is in no way meant to replace JavaScript. Rather, it's meant to augment the things that JavaScript was never designed to do. So let's look at some of the different advantages of WebAssembly and why you might want to use it. First, because WebAssembly offers strong type guarantees, it gives you more consistent and reliable performance than JavaScript. Then, with additional features like threads and SIMD, which we'll get more into later, you can also achieve speeds that are truly higher than what you can with JavaScript. When thinking about comparing baseline performance WebAssembly to JavaScript, I find this metaphor, which my colleague Surma came up with, really useful. JavaScript is like running along a tightrope. It's possible to go fast, but it requires a lot of skill, and it's possible to fall off the fast path. Whereas baseline WebAssembly is more like running along a train track. You don't have to be as careful in order to go fast. Another advantage of WebAssembly is its amazing portability. Because you can compile from other languages, you can bring not only your own code bases and libraries to the web, but also the incredible wealth of open source libraries built in languages like C++. Lastly, and potentially most exciting to many of you out there, is the possibility of more flexibility when writing for the web, specifically the ability to write in other languages. Since the web's inception, JavaScript has been the only fully supported option, and now through WebAssembly, you get more choice. Most excitingly, though, is the fact that WebAssembly is now shipping in all major browsers, making it the first new language to ship in every major browser since JavaScript was created more than 20 years ago. So now that we all are reminded of what WebAssembly actually is, I want to cover some of the improvements that we've been making directly in Chrome. One of the biggest requests that we've heard from our developers is the desire for faster startup time. To improve startup time for WebAssembly modules, we're starting to roll out something we're calling implicit caching. To recap, when a site loads a WebAssembly module, it first goes into the liftoff compiler to start executing immediately. It then is further optimized off the main thread through the turbofan optimizing compiler, and then the result is hot swapped in when ready. Now, with implicit caching, we also cache that optimized WebAssembly module directly in the HTTP cache. Then, after the user leaves the page and comes back, we load that optimized module directly from the cache, resulting in immediate top-tier performance. As the name suggests, implicit caching happens automatically. But there are two tips worth knowing and keeping in mind. The first is that code caching in WebAssembly works off of the streaming APIs, so make sure to always use compile streaming or instantiate streaming. The second thing is just to make sure that you're being cache-friendly. WebAssembly keys the cache based on the URL of the WebAssembly module, so if this changes on each load, you won't see any of the benefits. In addition to new features like implicit caching, we're also always making improvements to our WebAssembly engine. Here you can see how commit by commit, we've cut startup time by almost half since just the start of this last year. OK, so now that we've covered some of the improvements that have been made in Chrome, I want to get into some of the actual new language features of WebAssembly. The first feature that I want to talk about is WebAssembly Threads. Threads are a key part of practically all CPUs, and utilizing them fully and effectively has been one of the great challenges for the web until now. WebAssembly Threads work by relying on three specific things: web workers, shared array buffer, and atomic operations. Web workers allows WebAssembly to run on different CPU cores. Then shared array buffer allows WebAssembly to operate on the same piece of memory. Lastly, atomic operations, specifically atomic.wait and atomic.notify, let you synchronize your WebAssembly so that things happen in the right order. Google Earth adopted WebAssembly Threads with great success. They saw their frame rate almost double and their number of dropped frames cut by more than half. Foundation, a music editing studio, similarly adopted Threads to enable highly efficient parallelization. As they increased their number of threads, they saw their performance more than triple. One application that I'm particularly excited to share is coming to the web through WebAssembly Threads is VLC. They were able to originally compile their code base to baseline WebAssembly, but without Threads, they weren't able to achieve anything close to the performance that they needed. Now, thanks to Threads, they have a working prototype working directly in Chrome. So going back to our analogy from earlier, if baseline WebAssembly is like running along a train track, WebAssembly with Threads is like an actual train. You're achieving speeds that were previously impossible. Threads have been available in Chrome desktop since version 74. In Android Chrome and Firefox, Threads are implemented but not enabled by default. We're actively working with other browser vendors and the WebAssembly community to make Threads available in more places. Since Threads are not supported everywhere, it's critical to use feature detection before relying on their presence, which Ingvar will now show you how to do.
Thank you, Thomas. Unfortunately, WebAssembly does not have a built-in feature detection yet, although it's being actively worked on. For now, we created a JavaScript library instead that you can use to detect WebAssembly features supported by your browser. This allows you to build several versions of your WebAssembly module for different feature sets, just like you would for modern JavaScript bundles, and dynamically choose the ones that your browser can handle. For example, you can use threads function in order to detect whether your browser supports threads in WebAssembly. Then, you can use dynamic import to load either a version of your WebAssembly module and the JavaScript bindings that makes use of threads for optimizations, or a regular one for the older browsers. How do you build a version for threads in the first place? If you're using Scripting, you need to pass an argument -pthread during compilation, like you would to regular native C compilers. And it will automatically generate the WebAssembly module and the JavaScript glue necessary for creating, managing, and communicating with the web workers under the hood. If you are writing C, Scripting allows you to use common POSIX thread APIs, just like those available on native Unix platforms. For example, you can use pthread create with the handler function and arguments in order to start a new thread, and later in the code pthread join in order to wait for it to finish and read the results back. If you're writing C++, the good news is that Scripting implementation of standard thread APIs, just like in Unix, makes use of POSIX threads under the hood. And other high-level APIs, such as std async, makes use of std thread as a C++ standard level, so they all just work. This means that, for example, you can use std thread with closures in a C++ code, and it will load to the same pthread calls and handled by Scripting. Similarly, you can use std async APIs to spawn futures, which are quite similar to JavaScript promises, but allow you to spawn tasks on new threads. On the Rust side, the story is not yet so fleshed out, as you need to manually create web workers, send them the WebAssembly module and memory that you want to share, as well as rebuild the standard library with thread support. However, after jumping through a few hoops, you're able to even use popular multi-threading libraries like Rayon, like in this demo by Rust WebAssembly team. Here, they ported a ray tracer to split render it into several threads and compiled it to WebAssembly. You can see how with a single thread, it takes 1.7 seconds to render the entire image. But if you split work into, say, 4 threads, it takes only 0.8 seconds, making it more than 2 times faster. Another performance feature that is making its way into WebAssembly is SIMD. And I'd like to invite Thomas back to tell us what it is and how it can help us.
Thank you so much, Ingvar. So SIMD stands for Single Instruction, Multiple Data. And while this may not be a term that most web developers are familiar with, it's an absolutely key part of modern CPU architectures. So to explain SIMD, let's take this simple example of adding 2 arrays together into a third array using a simple for loop. Without SIMD, the CPU goes through this loop and adds the different elements together one by one, taking 4 full steps. Now with SIMD, the CPU is able to vectorize these elements and then take just a single CPU operation to add them together. This may seem simple, but it can have dramatic impacts on performance. To show the power that SIMD can deliver, I want to show off some of the work done by our colleagues at Google Research. They've developed several real-time ML models that can do everything from letting you try on fake glasses or puppet masks, doing dynamic background removal, and much more. One of the coolest demos is this hand tracking system. And here you can really see the difference that SIMD makes. Without SIMD, you're only getting about 3 frames per second, while with SIMD, you get a much smoother 15 frames per second, which makes all the difference. You can visit this link to check these out for yourself, or come by the sandbox to play with them. The Google research team looked at a bunch of their models and found that, in general, SIMD offered a 3x improvement on overall speed. The next example that I want to show off is OpenCV and some of the work done by our friends at Intel and UC Irvine. OpenCV is an extremely popular image analysis library that has tons of performance-dependent functionality. OpenCV can be compiled to WebAssembly and run directly in the browser. It can be used for doing things like card reading, replacing real emotions with emojis, and for all the Harry Potter fans out there, you can now have your very own web-powered invisibility cloak. You can visit this link to try them out, or again, come by the sandbox to see them there. This work has actually been fully upstreamed into OpenCV, and they even have a tutorial on how to set up OpenCV with Emscripten so that you can all play with this yourself at home. And all of this functionality can take advantage of threads and SIMD to dramatically improve performance. Here we can see the visual difference of first adding SIMD and then SIMD plus threads. And our benchmarking backs up this visually noticeable difference. When using both threads and SIMD together, common tasks in OpenCV can be improved by around 15x. And some of the benchmarks show even more dramatic improvements from threads and SIMD. For the OpenCV kernel performance test, using threads gives you a 3.5x improvement. And using SIMD gives you an even more impressive 9x improvement just by itself. And then when you take these together, it results in an overall 30x improvement to this performance test, which is truly staggering. So coming back to our train analogy, because who doesn't love trains? If WebAssembly Threads is like an old-style train, using threads and SIMD together is like a modern bullet train. So to show you how to actually take advantage of this in code, I'd like to hand it back to Ingvar.
Thanks, Thomas. To build code with SIMD and Emscripten, you need to pass a special parameter -m, which tells the underlying CLN compiler to enable a specific feature, followed by SIMD128, which is the feature name for the currently supported 128-bit SIMD operations in WebAssembly. In Rust, you need to pass the same feature name by a -c target feature compiler flag. The easiest way to do this on a real project using Cargo Wasm pack is currently through an environment variable Rust flags passed during compilation. Now that we've covered how to compile our code, let's see what it takes to actually use SIMD in our code. The good news is that in the simplest case, the answer is nothing. That is, unlike with threads, SIMD is something that compiler can often make advantage of and take care of without you having to modify any code at all. This compiler feature is called auto-vectorization, and it detects loops that perform same mathematical operations on array items independently. For example, let's take a look at the simple code in C, or an equivalent one in C++, or the same one in Rust. Such a loop operates on an array of numbers, check. It performs arithmetic operations, also check. And it clearly operates on them independently, also check. So the compiler should be able to make use of SIMD to process several elements at once rather than handle them by one, and make it faster. Let's see if it does. First, let's compile this code in any of the source languages without SIMD enabled, and take a look at the generated WebAssembly. We can see that our function got compiled to a loop that loads an item from an array, multiplies it by 10, and stores the result back. No surprises here. Now let's recompile it with SIMD enabled. We can see that, aside from our regular boilerplate, there is now another loop that loads 4 items out of an array, multiplies them by 4 instances of number 10, and stores the result back, also in just one operation. While it's a primitive example and not a real-world benchmark, it's interesting to see how such implicit optimization can help to achieve a consistent 3 times increase in performance of the generated code. In some situations, however, you don't want to leave it to chance to have your code optimized this way, or your data has a specific layout, or you just want more control over which features are used. This is where intrinsics can come in helpful. Intrinsics are special helpers that look like regular functions, but correspond to specific instructions on the target. For SIMD in Emscripten, they live in WASM SIMD 128 header and contain all basic operations for creating, loading, storing, and operating on the supported SIMD vector types. In Rust, the easiest way to use them is currently through an external packed SIMD crate, which is intended to be a prototype for a future standard library API. One important thing to keep in mind is that SIMD is still experimental and available only in Chrome under flag. So just like with threads, you need to make a separate build that makes use of SIMD, and then use a feature detection library to load it only if it's supported. Now that we've covered new WebAssembly features, we've got some exciting tool improvements to share with you too. First of all, earlier this year, LLVM, the compiler infrastructure behind projects such as CLang and Rust and lots of others, has stabilized and finished support for WebAssembly target. This includes both compilation of separate source files into WebAssembly object files, as well as linking them together into the final module. It's not very usable on its own. For example, while it allows you to compile separate C++ files into WebAssembly, it doesn't include any standard library and expects you to bring your own. However, it does provide a solid foundation for other compilers to build on. Let's take a look at Emscripten. Before this, Emscripten had to maintain a complex custom compilation pipeline and a fork of LLVM called fastcomp in order to parse an intermediate representation from CLang, compile it to AsmJS, and when WebAssembly came along, also convert it to WebAssembly. Having to work around LLVMs this way led to various incompatibilities in supported features, difficulties during upgrades, and suboptimal compilation performance. Now that the WebAssembly support has been properly integrated into the LLVM, Emscripten can leverage it to simplify the compilation process and focus on providing a great development experience, custom features, and a standard library, while all the core work for the features and optimizations can be continued to be developed upstream. As an example of improvement, switching to the native backend allowed Emscripten to significantly improve linking times with a small extra cost to the initial compilation. This particularly helps on incremental development, where you usually modify and recompile only like 1-2 files at a time, and all you need is a fast linking step. Some projects have seen as much as 7 times improvement in recompilation times in such cases. However, there were some compile time features unique to Emscripten that were previously handled by the earlier mentioned fork of LLVM and could be lost in transition. One of such features is asyncify. Normally, when calling from JavaScript to WebAssembly and then from WebAssembly to some web APIs, you expect to read the result back, continue execution, and eventually return to JavaScript. However, many long-running and expensive web APIs tend to spawn asynchronous tasks to avoid blocking the main thread. This includes timers, fetch API, web crypto API, and lots of others. Because WebAssembly does not have a notion of event loop, promises, or asynchronous tasks, to it would look like the external API has simply finished execution, so it can continue running users' code immediately, while the async task is still running in the background with no handlers attached. This is not what we normally want. We want to not only be able to start an asynchronous task, but also wait for it to finish, read the results back, and continue the execution afterwards. This is where asyncify comes in. I won't go too much into implementation details here, but what it does is compiles the WebAssembly module in such a way that it can suspend the execution, remember the state, and later resume from the exact same point when an asynchronous task has finished its execution. This is quite similar to await in JavaScript, but applied to native functions and with no changes to your own code. In order to use it from Emscripten, you need to pass a special parameter -s asyncify and specify which imports should be treated as asynchronous. The great news are Then in your code, you can use regular function imports and invoke them as any other functions, while Asynchify does magic under the hood. The great news is that with the transition to the upstream LLVM WebAssembly backend, this feature is not gone, but was extracted as a separate transform and can be now used from any languages, and not just C, C++, as long as they compile to WebAssembly. For example, you can simply invoke asynchronous JavaScript functions from Rust, which is particularly helpful for polyfilling standard synchronous system APIs available on other platforms. Since you are not using mscripting in this case, after you have compiled your module, you need to post-process it using wasm tool instead, and it will add all the necessary magic for suspending and resuming execution. Then you need some glue on the JavaScript side as well. We have created a wrapper for you that mimics a regular WebAssembly API, but allows you to instantiate modules with asynchronous imports and exports. To use it, first, you import it from Asynchify wasm npm module, and then you can use regular instantiation APIs, but with asynchronous imports and exports in addition to the regular ones. Since now your WebAssembly module might invoke asynchronous APIs in arbitrary points, all your exports need to become asynchronous too. So you need to prefix calls to your exports with a wait, and you're good to go. One particularly interesting use case for Asynchify, aside from external APIs, is in mscripting. Mscripting allows you to mark parts of your code as rarely used and split them to a separate WebAssembly module during compilation, and lazy load them only when it's invoked. This allows to keep your initial bundle small without any breakage to your own code and with minimal changes. To use it, you need to call a special function mscripting lazy load code. During compilation, it will extract any following code into a separate WebAssembly module. Then, during runtime, when or if that code is actually reached during execution, mscripting will use Asynchify to dynamically load the missing pieces and continue as if your code was never split in the first place. These are all great features, and it's amazing to see how WebAssembly is growing over time. However, with this feature growth, the surface area of potential bugs is expanding as well. When things go wrong, and we all know they often do, you want to be able to track where the problem occurred, reproduce it step by step, track the inputs that led to the issue in the first place, and so on. You want to be able to debug your application. Until recently, you had two options for debugging WebAssembly. First, you could get raw stack traces, as well as step over individual instructions in the WebAssembly text format. This helps somewhat with debugging of small isolated functions, but is not very practical for larger apps, where the mapping between the disassembled source and your original sources is less obvious. To work around this problem, mscripting and DevTools have initially adapted the existing source maps format, which was designed for languages that compile to JavaScript, for WebAssembly. This allowed to map binary offsets in the compiled module to the locations in original sources files. However, this format was designed for text languages with clear mapping to JavaScript's concepts and values, and not for binary formats like WebAssembly with linear memory, arbitrary source languages, and arbitrary type systems. This made the integration hacky, limited, and not widely supported outside of mscripting. On the other hand, many native languages already have a common debugging format that contains all the necessary information for the debugger to resolve locations, variable names, type layouts, and much more. This format is called Dwarf. While there are still some WebAssembly-specific features that need to be added for full compatibility, compilers like Clang and Rust already support emitting Dwarf information in WebAssembly modules, which allows us to start using it directly in DevTools. As a first step, we went ahead and implemented native source mapping, so you can start debugging WebAssembly modules produced by any of these compilers without having to resort to disassembled format or third-party scripts for source map generation. This integration already covers stepping in and over the code in any of these languages, setting breakpoints, and resolving stack traces. There's still much more we can do, though, such as pretty printing types or even evaluating expressions in these source languages. We are actively working on bringing this and many other improvements to the WebAssembly experience, so please stay tuned for the future updates. And thank you for your time today.